Good afternoon, everyone. This is the pre-launch news conference for the Radiation Belt Storm Probes to be launched for NASA and the Applied Physics Laboratory later this week on a United Launch Alliance Atlas V rocket. Here to talk about the upcoming launch is Mike Luther, the Deputy Associate Administrator for the Science Mission Directorate at NASA headquarters in Washington. Tim Dunn, the NASA Launch Director from the Kennedy Space Center. Fernthorpe, the Program Manager for NASA missions for the United Launch Alliance. Rick Fitzgerald, the RBSP Project Manager from the Johns Hopkins Applied Physics Laboratory. And Kathy Winters, the Launch Weather Officer from the 45th Weather Squadron at Cape Canaveral Air Force Station. And we'll begin first with our opening remarks from Mike Luther. Mike?
Thanks, George. Good afternoon. On behalf of NASA's Science Mission Directorate, I'm pleased to welcome everybody to the pre-launch and launch activities associated with the RBSP, our Radiation Storm Belt Probes, mission. We're all excited to be here today and looking forward to a successful mission. RBSP is a element of the Science Mission Directorate's program under the Heliophysics Division. It is under that division an element of the Living with the Star program, which is specifically designed to better understand the relationship between the Earth and its environment and the Sun. The twin spacecraft for RBSP will add a significant element and capability to the overall cadre of missions that the Science Mission Directorate flies across 4 scientific disciplines. RBSP in itself will focus its investigation on better understanding and ultimately predicting the response and changes associated with the Earth's radiation belt, or Van Allen belts as they're known. The twin spacecraft will fly in highly elliptical but slightly different orbits, thus enabling for the first time the kind of spatial and temporal sampling that will allow us to, in fact, do better scientific investigations and improve our modeling capability of the belts and their response to solar input. That spatial and temporal data can be combined with the data from another spacecraft, also an element of Living with a Star, called the Solar Dynamics Observatory, which was launched in early 2010, so that we can at one time see the solar impulse into the Earth's environment and the radiation belts, and then watch over time and space how those belts morph or change and respond. At the same time, the spacecraft will also contribute operationally, as their data will be delivered in near real time to users all over the world, so that those users can use the space weather data to protect sensitive ground-based as well as space-based assets that may reside out there. All in all, RBSP represents a giant step forward for the Science Mission Directorate and certainly for the heliophysics community, and we look forward to a successful launch. Thank you.
Thank you, Mike. And now to Tim Dunn, the NASA Launch Director from the Kennedy Space Center. Tim?
Thank you, George. I'm proud to be here today representing the men and women of the Launch Services Program here at Kennedy Space Center. The Radiation Belt Storm Probes, or RBSP mission, will be my third as NASA Launch Manager, and I'm thrilled to continue my Launch Director duties with the twin spacecraft launched on an Atlas V that will serve as the baseline for all radiation belt science for the next generation. This truly is a mission that would have thrilled my high school physics teacher, Mr. Skelton. Yesterday, we decided to delay the RBSP launch one day from Thursday to Friday. A test anomaly occurred Saturday night on another first stage Atlas engine, the RD-180, at the United Launch Alliance rocket factory in Decatur, Alabama. The RD-180 under test at Decatur experienced an anomaly in the actuator system that moves the engine for steering in flight. The combined NASA and ULA technical team jointly agreed yesterday that additional testing and assessment is required to verify the same anomalous condition is not present on RBSP's launch vehicle engine hardware. Due to this one-day delay, the Launch Readiness Review, or LRR, was moved from this morning to tomorrow afternoon. This allows our engineering and analytical teams adequate time to clear the RBSP vehicle for launch. NASA has a great record flying on the Atlas V. We've successfully launched 6 missions on this rocket. Missions to Pluto, Jupiter, the Moon, the Sun, and 2 spacecraft to Mars, most recently the Mars Curiosity rover. RBSP will be our 7th NASA mission on an Atlas V, the 28th Atlas V to be launched from Cape Canaveral Air Force Station, and the 32nd Atlas V overall. RBSP will launch on an Atlas V 401 vehicle from Space Launch Complex 41, also known as Slick 41. The 401 configuration has a 4-meter diameter payload fairing and no solid rocket boosters. Slick 41 is proud to have hosted 27 Atlas V launches to date. Now I'd like to show you a video of the ULA crew building up the Atlas V launch vehicle at the pad. Please roll the tape. Here we see the RBSP first stage after it was offloaded at Port Canaveral on its way to the Atlas Spaceflight Operations Center, or ASOC. Made in Decatur, Alabama, the first stage is transported to Cape Canaveral via the ship, the Mariner. This offload and transport happened in the middle of June, on June 16th. Here we see the second stage of the Atlas V, the Centaur. This offload occurred at the end of May this year, on May 24th. It's being transported to the same facility, the ASOC, on Cape Canaveral Air Force Station, where it will be electrically connected to the first stage for horizontal checkout. That checkout occurred during the last 2 weeks in June and the first week in July. After that checkout, you see the first stage booster being transported from the ASOC out to the VIF, which is the vertical integration facility shown here. The VIF is located near Complex 41 and is where we build up and process all of the Atlas V vehicles. You'll see here the erection sequence using the VIF crane. The overhead crane lifts the first stage booster and brings it into the VIF and sets it down on the MLP, or mobile launch platform. This is a nice view from the tail side looking up, seeing the power plant RD-180 engine there. 3 days later, in the middle of July, we transported the Centaur second stage out to the VIF for its sequence of erection and mate to the top of the first stage of the Atlas V. The power plant for the second stage is the Pratt & Whitney Rocketdyne RL-10. So you'll see the erection sequence here using the same VIF overhead crane under the watchful eye of ULA employees. We erect the second stage Centaur and bring it in and set it down on top of the first stage. A nice view there of the RL-10 on the aft side of second stage. The next shot you'll see is of the completed first and second stage in the VIF just days before spacecraft arrival. In the early morning hours of August 10th, we transported the spacecraft out to the VIF. Here you see the twin RBSP spacecraft encapsulated by the 4-meter fairing. After rollout from the spacecraft processing facility, we erected the encapsulated assembly and mated it to the top of Centaur. And there you see the completed Atlas V vehicle as it sits today. The RBSP launch campaign has gone very well. Over the past 10 days since RBSP mate, the Atlas V team has been busy with launch preparations. Last Tuesday, we performed the final integrated systems test with the spacecraft and rocket. Last Thursday, the combined NASA and ULA launch team held the flight readiness review, where we assessed the preparations of the launch vehicle, range and facility assets, and the readiness of the twin RBSP spacecraft. Then, on Friday, we performed a successful mission dress rehearsal to exercise and prepare the entire ULA, NASA, and Air Force Atlas V launch team. Tomorrow, we will conduct the launch readiness review for the mission, where senior NASA, ULA, and Air Force management will assess readiness of the rocket, spacecraft, and range to proceed with launch on Friday morning. On Wednesday, we will begin final launch preparations at approximately 10 a.m. Eastern Time by rolling the Atlas V on its mobile launch platform approximately 1/4 mile from the VIF to Slick 41, and then loading the highly refined kerosene RP-1 fuel in the first stage fuel tank. Thursday will serve as a crew synchronization day to prepare the launch team for arrival on console just after 10:30 p.m. Thursday night. The crew will perform final preparations of vehicle power on and electrical checks, followed by cryogenic tanking of the first stage liquid oxygen and second stage Centaur liquid oxygen and liquid hydrogen, beginning at 1:40 a.m. Friday morning. Final engine slews will then be performed after tanking, and we will be ready for launch early Friday morning at 4:07 a.m. Eastern Time with a 20-minute window. In summary, after LRR tomorrow, the Atlas V rocket will be ready, and the launch team is prepared and excited to launch these radiation belt storm probes. Back to you, George.
Thank you, Tim. And now to Fernthorpe, the program manager for NASA missions from United Launch Alliance, to talk about the ULA role and the flight of the Atlas V. Fern?
Hey, thank you, George. Good afternoon. On behalf of Michael Gass, our President and Chief Executive Officer, and the 3,600 men and women of United Launch Alliance, I'm honored to be part of the team that will launch RBSP. This will be ULA's 7th launch of the year. Tim mentioned it's also the 32nd Atlas V launch, and it'll be the 63rd launch for ULA overall. Since the inaugural EELV flights in 2002, Atlas V and Delta IV vehicles have launched more than 50 times, delivering vital national security missions for the U.S. Air Force and the National Reconnaissance Office, science and exploration payloads for NASA, and imaging and communication satellites for commercial companies. We've worked together with our NASA Launch Services Program customer on numerous missions, including the recent Mars Science Lab, which was launched on an Atlas V here from the Cape just last November, and of course had a spectacular landing recently on the surface of Mars. As for all of our missions, the team has worked tremendously hard to get us to this point, and we are almost ready to launch RBSP on its mission to help us better understand the effect of solar activity on our near-Earth environment. This mission will be launched on an Atlas V 401 with the 4-meter fairing and no SRBs. And the booster stage will be powered by the RD-180 engine provided by RD Amros, and we'll have a Pratt & Whitney Rocketdyne RL-10A-4 engine on the Centaur upper stage. And now I'd like to show some animation of the launch sequence to give you a preview of what to expect on Friday morning. Okay, the vehicle stands about 190 feet tall on the pad, and when we light the RD-180 engine, it'll be putting out about 860,000 pounds of thrust at liftoff at sea level. The first major event that you'll see during this flight, since we don't have any SRBs to jettison, will be the depletion of fuels in the main booster tank, the shutdown of the main engine, and the separation of that Atlas booster stage. That will occur roughly 4 minutes into flight. After we separate that booster stage, we'll prepare the Centaur engines for ignition, and we'll light them for the first of 2 engine burns. There you see the retro rockets firing to separate the booster stage. That's the chill down sequence for the RL-10 engines, and then we'll light the engines. About 8 seconds into that first engine burn, we will also jettison the payload fairing. The total duration for this first engine burn will be about 9 minutes and 15 seconds. And that will place us into a parking orbit coast, which is a pretty typical mission profile for an Atlas vehicle. That coast is almost an hour. It's about 55 minutes. At the end of that coast, we'll be in position for the second engine burn, so we'll light the Centaur engine again. That'll be a shorter burn, about 4 minutes and 40 seconds. And after that, we will orient the vehicle, do a spin up and separate the first of the two spacecraft. We will then reorient again, use the settling thrusters to change the orbit just slightly for that second spacecraft, and we'll separate it about 12 minutes later. And then following separation of the second spacecraft, we'll do the usual contamination and collision avoidance maneuver to prevent any possibility of recontact of the Centaur upper stage with the spacecraft. We are proud to serve a critical role in delivering one-of-a-kind NASA payloads to orbit in support of the global science community. ULA is focused on perfect product delivery for RBSP and for every mission we launch for NASA and for all of our other customers. Perfect product delivery includes a relentless focus on mission success, a focus on one launch at a time, and continuous improvement in meeting all of the needs of our customers. This mission is the culmination of years of hard work by NASA's Launch Services Program, NASA's Goddard Space Flight Center, the Johns Hopkins University Applied Physics Lab, and the ULA launch team. Once again, I want to thank all of our mission partners who've worked with us tirelessly to make this launch a success. Back to you, George.
Thank you, Vern. And now to Rick Fitzgerald, the RBSP project manager from the Johns Hopkins Applied Physics Laboratory. Rick?
Thank you, George. Well, I'm pleased and honored to be here today to represent the RBSP project, which is considered to be part of the program that Mike described, the Living with a Star program. Our team members include the Applied Physics Laboratory, which is my home institution, but all of our instrument providers. So we have principal investigators from the University of Iowa, the University of New Hampshire, the New Jersey Institute of Technology, and the University of Minnesota. And we are also partnered with the Goddard Space Flight Center, which is where the LWS program office resides, and also a contributed instrument from the National Reconnaissance Office. So without all these instrument partners and teaming arrangements, today wouldn't be possible. So I'm really happy to be here to represent that entire group. What I'd like to do is talk a little bit about picking up with the sequence after launch that Vern just described, and then come back and talk a little bit more about the science of the mission. And I have some video about our processing that we've undergone while we're down here after shipping from APL. So the first thing is the launch sequence. So you saw that we have two spacecraft. We get dropped off after a spin-up of the Centaur stage. The A spacecraft will separate at approximately 80 minutes after launch over Hawaii, and the second spacecraft, B, will separate just a few minutes after that. And as Mike pointed out, we will be in slightly different orbits, and that's by design so that we can achieve the science that we've all been waiting for decades. After we separate, the spacecraft maintain a spin rate. The first actuation that really occurs is we open up our solar panels and go power positive by getting sunlight on our solar panels and start charging our batteries again. Following that, we deploy some booms on the end of two of those panels, which are the emphasis instrument, their magnetometer, which is also critical to not only the science but also our spacecraft operations. So those things happen early on in the sequence. We launch with our spacecraft subsystems partially on, and the first thing we do is we check out the RF subsystem and make sure that we're seeing all the link margins that we expect to see as we pass over the various ground stations. We also have our spacecraft processor partially on, and of course our power subsystems. We will then check out our guidance, navigation, and control. And then there's a carefully sequenced 60-day commissioning period where in this choreographed activity we carefully turn on each instrument one by one. And all this has been very carefully coordinated with all the PIs on the mission. At the end of 60 days, all the deployments will have happened, all the instruments will be turned on, and we will be ready to start the science of the mission. One thing to point out is 2012 is an important year for us because we're launching in a period of high solar activity. So we're nearing solar max, which means we stand the best chance of seeing a lot of solar activity excite the radiation belts, and that's exactly what we want to see happen. So a little bit about the science, and you will get a full science briefing later on. But you will hear that we've been waiting for this mission for decades. The Van Allen belts were discovered in 1958, and since that time, we know something about the radiation belts, but not enough. This mission is designed to really understand the whole solar interaction with radiation belts and understand why they are excited and sometimes why they're not. And the mission design itself is part of that equation. So we're at 10 degrees inclination in a highly elliptical orbit so that we cruise in and out of both radiation belts throughout the mission. The satellites lap each other, and you'll hear more about that, about why that's important for the measurement that we're making. And the 2-year mission life allows us a full cycle of these lapping rates and allowing us to precess around back to the place where we injected into orbit so that we see kind of a full season of activity in a sense. What I'd like to do next is talk about the processing that we've undertaken since we've come down here to the Cape. And if you'll start the video, I'll walk you through that. This is the C-17 Air Force plane that brought us safely down to the Cape. So we trucked from the Applied Physics Laboratory over in Laurel, Maryland, over to Andrews Air Force Base, loaded onto the C-17 in the wee hours of the morning, and arrived here at the Cape. You can see there the 2 satellite canisters under purge to keep them protected from the environment. We arrived at Astrotech just outside the KSC gates here. This happened on May 1st. You can see our technicians carefully unwrapping both spacecraft and days later opening up the spacecraft. So we need to make sure after we arrive that we didn't have any disruption to the spacecraft due to the ride. Here's some black light cleaning. The black light allows us to see all dust particles all over the spacecraft and clean those appropriately. This is one of our tests we perform, the magnetic swing test, where we actually swing the spacecraft through a magnetic field to make sure that it's magnetically silent. We also went through a spin test. I mentioned that we spin on orbit at about 5 RPM, so we have to make sure we're still well balanced. Here's some more cleaning in the black light. Here we are with some of the panels raised and getting ready for a deployment test with the solar panels, and you can see the emphasis instruments there. And there's a G-negated test of the solar array deployment with the booms for the emphasis instrument. The high bay that we were in is tremendous. It's a great facility there at Astrotech. You can see all of our techs in clean room garb, plenty of space to work on 2 spacecraft. Here's the emphasis deployment, G-negated. So it gives you an idea of what that looks like when we deploy that boom shortly after we get on orbit. And here we are with some of our final closeout activities and our mission assurance folks taking a careful look at the spacecraft as we move from step to step. All the scripts that they have on their laptops, and also all of the motion tests that have to be measured and compared against what we expected. This is a spacecraft stack being moved on the dolly to get ready for encapsulation into the fairing, and there you can see the second half of the fairing closing us up for the last time right there. That was a big day for us that happened last week. The team is assessing to make sure that we're all in good condition, and we're backing up, getting ready to be transported from Astrotech over to the VIF. There's our team carefully loading onto the truck, and again in the middle of the night moving over toward the VIF so that we don't have any vehicular traffic to worry about, and the caravan that's carefully motoring us at a safe 7 miles per hour over to the VIF. So again, I'd like to say how excited we are about this mission. This culminates more than 5 years of effort. And in fact, the first planning stages from the science happened in 2001. There was a meeting to talk about what the science would be and what we wanted to measure and how we wanted to do that. So many, many years of activity preparing for this day. and in fact, since the 50s, to try to unlock some of the mysteries of the Van Allen belts. So again, on behalf of the team, thanks for everyone's support to get us to here, and we're looking forward to launch day on Friday, when we're going to see all this work finally come to fruition on orbit. George.
Thank you, Rick. Now to Kathy Winters, our launch weather officer for the 45th Weather Squadron at Cape Canaveral Air Force Station. Kathy.
Thank you, George. Well, we are looking for afternoon thunderstorms like we've been seeing each day here in Florida. It's pretty typical for this time of year. We do have a strong upper-level trough that's been digging down in the eastern U.S., and it's actually going to dig a bit further in the next few days. And so we expect for all the thunderstorm activity that does occur in Florida to migrate towards the east coast, here towards us. So we continue to expect to see afternoon storms in the area. And on as we get into launch day, the day before launch is Thursday, we'll be seeing those storms, and then we'll have some residual cloud cover that will linger in the area in the overnight hours, and that just causes us some concern that we could violate the thick cloud rule for launch. The other area that we're watching, there's an area in the tropics that we're keeping an eye on as well. It's a couple hundred miles east of the Lesser Antilles. Let me go ahead and show you a satellite picture to kind of explain where that is. You can see on the satellite picture a few hundred miles east of the Lesser Antilles, there is a wave that's developing. This is right now has an 80% chance of tropical cyclone development within the next 48 hours, according to the Hurricane Center. So it does pose a risk for the Lesser Antilles and Antigua, but it should move through that area on Wednesday, be off to the west, and still have another day to recover there. And they may stow the antennas if they need to, but then they can redeploy them and be ready for launch. For the eastern U.S., there is that trough there, so we'll be watching for that residual cloud cover. You can see it on the satellite picture, and there's a boundary associated with that as well in northern Georgia. That is going to sag down on Thursday into the area. And so with that, we have a little bit more concern for cloud cover for Friday morning than we typically do this time of year, just because that additional boundary that's going to be lingering in the area. So right now, our main concern for launch is a violation of the thick cloud rule. We have a 40% chance of that launch commit criteria violation. And the thick cloud rule, we have that rule to prevent triggered lightning. It's not natural lightning created by a thunderstorm, but lightning that can be triggered due to a rocket launching through elevated electrical fields. Now, if we happen to delay 24 hours, the big question mark will be what is that tropical wave going to do? Right now, some of the models bring it, most of the models bring it actually straight west, but then some of the models actually bring it a little bit more towards the north and head it into Hispaniola and then just southeast of southeastern Cuba as we get into Saturday morning. What that means for us is that the ridge actually migrates back up to the north, and we get into more of an easterly flow pattern, and that can cause some isolated showers to occur on Saturday morning. So our main concern, if we happen to delay 24 hours, would be a cumulus cloud rule violation that's associated with these isolated showers. And we'd be mainly watching for any cumulus clouds within 10 nautical miles of the launch pad and looking at how tall those clouds are to see if they violate the rule. And we don't expect any lightning with those, but again, it's more of a triggered lightning concern, and that's what a lot of our lightning launch commit criteria rules are about, is triggered lightning. So overall, still a better chance than not when it comes to weather. Still a 60% chance of having go weather for launch, but there is some concern for thick clouds on the morning of launch.
All right, thank you, Kathy. And we're ready now to take questions. Please give your name and affiliation when the microphone comes to you. And we'll start here in the front with Marcia.
Marcia Dunn, Associated Press, probably for Mr. Fitzgerald. Why has it taken so long to launch a spacecraft to the radiation belts to get a good handle on what's going on there? And if you could give a little history of perhaps other craft that have done research in this area, and how are you going to be protecting these two craft from a pretty hazardous environment?
Thank you. Some of the details about the history, I think some of our science folks could give you better. But I will say that there was a mission called CRESS that did go to the radiation belts. It was a single spacecraft, and it unlocked some of the mysteries of the radiation belts, but left additional questions. For instance, this issue about seeing a lot of solar activity that you would expect may excite the radiation belts, but in fact did not. Why did that happen? We don't understand that. So the Radiation Belt Storm Probes mission, this twin satellite mission, is supremely equipped to make the measurements that would help us understand what those what the processes are that are going on within the belts and due to coronal mass ejection. With respect to how do we protect the mission, so that's a great question too. I started off with an analogy. I'm a runner, and as a runner, there's this slogan you see at track events that says, "My sport is your sport's punishment." And on this mission, our mission is other missions' punishment. We're going to a place that other missions try to avoid, and we need to live there for 2 years. That's one of our biggest technical challenges. And so we did that on many different levels. The first is we have a lot of shielding of all electronic boxes. So we have 350 mils of aluminum shielding around our electronics. That's about 1/3 of an inch to give you a better feel for that. And that helps protect against some of these highly charged particles from penetrating our sensitive electronics. In addition, the electronics themselves, we selected a lot of radiation-hardened parts. So you can purchase those. They are more expensive than standard parts, and they also give you some level of protection against both single-event upset and cumulative radiation over time. And so those things are the primary mechanisms for us to protect against the environment that we're going to fly in. We also have some other specialized things that we've done to help with the science measurements. So we need to be magnetically quiet, as you saw in that magnetic swing test. So basically that was kind of like walking through a magnetometer at the airport. If you had no metal in your pockets, it doesn't go off. In that test, we're also trying to make sure that the spacecraft itself is not inducing a magnetic field that would be picked up by our emphasis instrument, and therefore cause noise on that measurement. So there are a lot of unique things about the mission that we had to think about and design into in order to make the sensitive measurements that we're going to make.
Any other questions for our pre-launch panel here? Justin.
Hi, Justin Wright with spaceflightnow.com. Two for Tim. Are you physically doing anything on the RD-180 here, on the vehicle here, or is it more of a paperwork analysis type of effort? And would you expect this issue is going to be resolved by tomorrow's LRR?
Yeah, let me answer that, and I'll let Vern add a little more. We're doing both, Justin. We are doing testing on the RBSP hardware today. We are doing engine cycling tests, and as well as data review. We're doing a combination data review from the Decatur anomaly that occurred over the weekend through the joint team, the ULA team, NASA, as well as Pratt & Whitney Rocketdyne. And when the technical team met yesterday afternoon, I would categorize it as we did have high confidence that we would be able to get through this, but we did want to perform today's confidence testing as well as completed data review. Vern? Anything to add?
No, I think Tim provided a good summary. We think we understand what the issue is. The testing that we're doing today will build up some separation between this engine and the engine in the factory where we saw the issue. Even though we think we know what the issue is, we're going to move very slowly, very carefully today. The testing itself that we're going to be performing on the engine lasts about 4 hours, but some of our folks have about a 14-hour day ahead of them because of all of the review and thought and preparation that goes into that to make sure that we're really on the right track. But I would say overall we're pretty optimistic that we know what's happening.
Quick spacecraft question. Are you actually going into your final orbit when you come off of the Centaur, or do you have to do any sort of raising burns in your initial 60-day period?
Essentially, we're injecting into the orbit that we want to be into. Of course, we'll assess that after we get dropped off and find out where exactly we are. But the intent is that we'll begin our deployments that we're in where we want to be. And as I said, over the next 60 days, we will be turning on the science instruments and assessing what we have and where we are. But the direct answer to your question is yes, we're essentially where we want to be when we get dropped off.
James?
James Dean with Florida Today. For Kathy and Tim, I think, isn't space weather part of the launch forecast that you provide? What can you provide? Why do you need it? And assuming the goal here is eventually to do that better, how helpful would that be for you?
It is. We do look at proton flux units, and right now it seems that this week so far is looking relatively quiet. There's a couple of sunspots that are rotating around the side of the sun that we're going to be watching for solar flare activity, but so far it's a little bit far out to tell if those are going to be active enough to generate a flare, and we'll get a better feel for that as we get a couple days before launch. But we will be watching for proton flux activity associated with solar flares. And you can give the why, I guess.
Yeah, we do monitor the proton flux. It is a critical launch constraint for us. Highly energized particles would tend to cause single event upsets or bit hits in flight computers on launch vehicles. So we do have a constraint for that, and we do monitor that prior to launch.
Just following up, can you speak just in general about the frequency of space weather events affecting spacecraft, space-based assets, I guess. Obviously, again, that's a goal of better prediction, is to protect those types of assets, but it's not, doesn't seem very often that I've heard of a spacecraft being damaged or disabled from that sort of thing. So just trying to get a feel for how common this is, and
Yeah, I could speak from the launch vehicle side of it because we do monitor for that type of activity in the atmosphere. We're generally protected on the launch vehicle, so we don't tend to experience very much during the launch phase of operations. For the spacecraft side, Rick, you may have some knowledge of past upsets of spacecraft on orbit and how that affects them.
Yeah, it's a bit of a conundrum. So we're worried about space weather when we're launching a mission to give us space weather. It's kind of like being worried about driving through snow to go skiing, right? So we are going to watch the forecast. We're a little bit more resilient than the launch vehicle is for the space weather because of the way we're built. With respect to space weather events, sometimes you don't hear about them because on-orbit assets try as best they can with the space weather predictions that we have. They can turn off some sensitive electronics in order to avoid single event upsets and actual failure. And that's another part of our mission, is to be able to give better space weather information that other agencies and other spacecraft providers can use for their on-orbit assets. As far as making the news, it makes the news when it affects the general population the most. So when GPS is affected, it can affect so many people in so many ways. It can affect airliners. It can affect communication. It can affect a lot of things. And so when those kinds of things happen, you hear more about it. Or a communication satellite, when a comm link is interrupted in the middle of an important event. That kind of stuff makes the news. A lot of things, a lot of science measurement spacecraft don't necessarily make the news if they have an event that they are dealing with. So that's something I can't really answer about when you hear about it and when you don't. That's more or less controlled by the media. But it is a real thing that you have to worry about, and this mission is all about helping everybody understand what's really out there that they need to deal with.
Maybe I could contribute a little something there, just so you understand. The Science Mission Directorate operates some 50-odd missions across our four disciplines. I get a report anytime one of those missions operations is disrupted. Anecdotally, I will tell you that that's probably about once a month. A mission will not the same mission every month, obviously, but of that collective group of missions, probably 10, 12 times a year, we'll have a satellite either have a disruption, we refer to them as single event upsets, or we do have some missions who, as Rick said, take proactive action if we understand that there's a solar event that's taking place in order to avoid a problem. The impact of that may not make the press because it doesn't impact people day to day, but we're talking about space assets that cost hundreds of millions of dollars to collect science data we don't like losing one bit, I mean that literally bit of science data. And so it's a very disturbing event when we have to shut an instrument down or a spacecraft down, bring it back up again. We can recover from those. We always do, or almost always do. But the recovery means that you've lost some time period of data. So it's not an insignificant impact to the on-orbit assets.
Marcia, follow-up?
Yes, two quick follow-ups. The $386 million cost of the mission, does that includes the launch costs?
The
No.
total NASA mission cost is $686 million, and that does include the launch vehicle and all phases of the mission.
And do you have any plans after launch to name A and B? Or will they always be A and B?
There are some plans under discussion from NASA headquarters. I don't know, Mike, if you want to address that.
We have a process that we have to go through. There's been a proposal. It has to be vetted before we can make an announcement. So I am not prepared to make that announcement here. But there's some proposals that are being considered for names that have to go through a process.
Definitely after launch.
Yeah,
Definitely
right.
after.
After the successful launch and so on. Mm-hmm.
All right. I think we have someone following on the phone as well. Michael Wall, did you have a question? And if you do, if you can give your affiliation.
Oh, yeah. Hi, this is Mike Wall from Space.com. Can you hear me?
We can hear you.
Okay, thanks. Sorry. Yeah, I'd just like a little more information about the anomaly. I mean, is this something that you guys have seen before? I mean, in the rocket, and yeah, I mean, what are some of the steps that you're taking? I mean, I know you sort of outlined them, but could you go into a little bit more detail about sort of how you're going about fixing this?
You want me to take that?
Yeah, I'll let you take that.
Okay, this is Fernthorpe with United Launch Alliance. We can tell you that the anomaly that we saw was on a hydraulic system actuator, essentially. And we've seen similar data signatures before on similar actuators. And that's the primary reason why we think we understand what's going on. That data signature combined with a detailed understanding of the internal workings of this hydraulic system. I'm really not at liberty to go into too much more detail than that, other than to say that even though we think we understand it, we think we've got a good hydraulic system on the engine for the RBSP mission. We're not going to take anything for granted or make any assumptions we don't have to. We're going to go in and do this screening test today that will give us confidence that the engine for RBSP is not susceptible to the same type of anomalous data signature that we saw back in the factory on another engine.
Thank you.
All right, back here for any last questions. All right, in that event, we're going to pause long enough just to change our players here on the dais, and we'll go into the RBSP mission science briefing. Thank you.